Today we're going to talk about some very important subspaces, the null space and the column space of a matrix. Next time we're going to next time we're going to talk about row space. We definitely will talk about row space in this chapter, just not positive it's the next section. So let's review what a subspace is. A subspace of a vector space is a subset that obeys these three axioms, or it has these three properties. The zero vector is in H. H is closed under addition, meaning if you take two vectors u and v in H, then their sum remains in H. And H is closed under scalar multiplication, meaning if you take a vector in H and any scalar, that's a real number, multiply that vector by the scalar and you remain in H. So for example, show that this subset of R2 is a subspace. And this is the set of vectors that look like 2a, a minus b. All right, so let's write the vector 2a, a minus b as 2a plus 0, negative b. And now let's pull out the a, 2, 1. And let's pull out the b, 0, negative 1. Okay, and after I do that, I see that H is actually the span of two vectors. H is the span of the two vectors 2, 1 and 0, negative 1. Set of linear combinations of those two vectors. But last time, theorem 1, we saw that any span is a subspace. So any span of vectors from a vector space forms a subspace. So this is a subspace. All right, another vector space we looked at last time was Pn, which was the set of vectors, polynomials, of degree less than or equal to n. So P3 is the set of vectors, set of polynomials of degree less than or equal to 3. So this vector or polynomial is in P3 because it's got degree 0. This is in P3, it's got degree 3. This guy's not because it's got degree 4. And this guy's not because it's not even a polynomial. It's a continuous function. All right, a very important vector space is the set. If A is an M by N matrix, A takes vectors in Rm to vectors in Rn. So multiplication, if you take a vector x, Ax, x is in Rm, Ax will be in Rn. The set of vectors in this is backwards, sorry. If A is M by N, this is N, and this is M over here. The set of vectors in Rn, so the set of vectors over here that go to 0 over here, that set of vectors forms a vector space. So the set of all x in Rn such that Ax equals 0. We can verify this very easily by just looking at the three requirements of being a subspace. So this is going to be a subspace of Rn because because these vectors come from Rn. So the first thing, A times 0 is 0. So 0 is in this space. I'm calling it H right now, but I'm about to call it the null space. So 0 is in H. If I take two vectors in H, so two vectors that A sends to 0, I have to show that A sends their sum to 0. So that's really easy because matrix multiplication is linear, so it's going to distribute over the x and the y. But by supposition, Ax is 0 and Ay is 0. 0 plus 0 is 0, so the sum of two vectors in H is still in H. Finally, if I multiply a vector in H by a scalar, I still have a vector in H because scalars can come out of matrix multiplication. Ax is 0. 0 times c is still 0, so Cx is in H. All right, that space is is very important, and we call it, that's this definition here, the null space. The null space of an M by N matrix is the set of solutions to AX equals 0. So it's a set of all X such that AX equals 0. You need to know this definition. And a theorem is that the null space is a subspace of Rn. And we just proved the theorem. Proof would be number 4 above. We showed that it's a subspace. Now, if you're talking linear transformations, some people will call the null space the kernel. So instead of calling it the null space of A, you would say it's the kernel of the linear transformation that takes Rn to Rm. You don't have to memorize that. I just thought I'd throw that out there because it's interesting. So let's look at some examples. Show that H equals this set of vectors is a subspace of blank by showing it's the null space of a matrix. All right, well, what could it possibly be a subspace of? These are vectors in R4 because there are 4 entries. So that's the only possibility to put here. So we want to show we have a subspace of R4. So let's write this linear system the following in the following way: 2a plus 3b minus c equals 0, and then negative a. I'm going to do this in order: negative a plus b plus c minus d equals 0. All right, well, that's a linear system. It's homogeneous. In matrix form, I can write that as the matrix of coefficients 2, 3, negative 1, 0, and then negative 1, 1, 1, negative 1. That matrix times the vector A, B, C, D equals the vector 0, 0. So that would be the matrix form of that linear system. So if I call this matrix here A, then H is simply null A. H is null A. It's a set of vectors that A kills. And by the previous page, null A is a vector space. And in this case, A is 2 by 4. So A maps R4 to R2. You can see that it takes vectors in R4, A, B, C, D, to vectors in R2. And so H is null A, and null A is a subspace of R4. Okay, next one. Is H equal to the set of vectors A, B, C such that this equation is true, a subspace of R3? You might think, well, we'll do the same thing we did above. We'll show that H is null A for some matrix A, but there's going to be a problem because of this 4 here. The answer is no, and I'm going to go with the low-hanging fruit. When you want to show something's not a subspace, if you can show the 0 vector is not in there, it's the quickest way to do it. And sure enough, 0, 0, 0 is not in H, since if I take 2 times 0 plus 3 times 0 plus 0, I get 0. That's not equal to 4. So the answer is no there. Okay, the next example is pretty important. Let A be this matrix. Write A as the span of a set of vectors. All right, so it's not at all obvious how to do this. What we want to do is find the solutions of AX equals 0. So we want solutions of AX equals 0. So the way that we do that, since probably the first week, is to augment A with the 0 vector and reduce to reduced echelon. And just to save us some time, I already did that. It got us all the way down to reduced echelon, and you can verify my calculations. And I come up with this, and I see there are 2 pivots, in the first column and the third column. So x2 and x4 are free. You might want to pause the video, make sure you can write down in parametric vector form the solution of this system. See if you can do it, because that's what I'm about to do. All right, x2 and x4 are free. So remember how to write down a solution in parametric vector form. You start at the bottom. You start with x4. And I know there are 4 variables because there are 4 columns aside from the augmented column. So x4, that's free. Let's call it t. x2, sorry, 3 comes before 4. X3 is 6t. x2 is free since there's no pivot in the second column, so I'll call it s. And finally, x1 is negative. Remember, the colon is like an equal sign, so negative 2s minus 13t. All right, so in parametric vector form, x bar equals, I'm going to have an s vector and a t vector. The s vector is negative 2, 1, 0, 0. And the t vector is going to be negative 13, 0, 6, 1. Okay, now we go back and we read the question because we've kind of forgotten what we're doing. Write null A, that's the set of solutions of AX equals 0, as a span of a set of vectors. Well, here's what any guy in null A looks like. So null A, now it's very easy to do. Null A is the span of the 2 vectors you see there. Negative 2, 1, 0, 0, comma, negative 13, 0, 6, 1. That's the set of all linear combinations of those 2 vectors. Well, that's exactly what vectors in null A look like. So we've done it. Null A is the span of those 2 vectors. When we start talking about basis, which might be the next section, couple of important generalizations. First of all, those 2 vectors are automatically linearly independent because the only solution to x bar being 0 would be both s and t are equal to 0. So I have 2 linearly independent vectors in that set, and the number of vectors in that set is the number of free variables in AX equals 0. Because for each free variable, you get a letter. Like if there had been a third free variable, I would have had one of these guys equal r. So RST, that would be 3. Each letter is going to correspond to a vector in your spanning set. So the number of vectors that span null A is the number of free variables in AX equals 0. And when it comes to it, I'll remind you of that information so you don't have to memorize that right now, but we'll see that that's important later. All right, so that's the null space, set of solutions to AX equals 0. Let's talk about the column space of A. So remember, if A is m by n, A we can think of as a mapping from Rn to Rm. And that mapping is multiplication by A. X goes to AX. X goes to AX. The column space is simply the span of the columns. So you look at the columns of A, the span of those columns is the column space, and that is a subspace of Rm. So a couple things here. First of all, I know it's a subspace because it's the span of a set of vectors. And we saw last time that the span of a set of vectors is always a subspace. Second of all, why is it in Rm? Well, the columns live in Rm. So let's just do a concrete example here. If A is 2 by 3, so 2 rows, 3 columns, 1, 2, 3, 4, 5, 6, I can think of A as mapping R3 to R2. The columns, look at the columns, where do they live? They live in R2. Each column has 2 entries. Call A lives over here. col A lives over here. So null A lives over here, and col A lives over here. They live in different places. We're talking about two subspaces today associated to an m by n matrix. One of them lives in the domain, and one of them lives in the what we call the codomain. All right, and again, I'm gonna go through this again many times before the end of this chapter. Let's look at some old results in a new language. One old result we have way back from chapter 1 was that AX equals B has a solution if and only if B is a linear combination of the columns of A. Another way to say that is AX equals B has a solution if and only if B is in col A, because col A is the set of linear combinations of the columns of A. So it's a quicker way of saying that. In addition, col A is the set of all B such that AX equals B for some X in Rn. So it's the set of guys over here that get hit by A when A, so AX equal B, it's the set of B's such that that has a solution. AX equals B, so here's an old result. AX equals B is consistent for all B if and only if the columns of A span Rm. That's the same as saying col A is all of Rm, because col A is the span of the columns. All right, so let's look at our dimensions more carefully. A is m by n. So again, A maps Rn to Rm. I always write that down. If A is m by n, you got to reverse the dimensions. A takes a vector in Rn. Ax will be in Rm. So null A is a subspace of Rn. Null A lives over here. Whoops, that goes the wrong direction. There we go. Null A lives over here. It may or may not be all of Rn, I don't know. And then col A lives over in Rm, and col A may or may not be all of Rm. It will only be all of Rm if Ax equals B is consistent for all B. And we know that's in general, that's not true for every matrix. Okay, so here are a couple of examples. Show that this vector here is a subspace of blank by showing H equals col A for some A. Well, these vectors are in R3, so that's the only possibility for what could go here. And if I take the vector x minus 2y, 3y, x plus y, I can write it as x times the vector 1, 0, 1 plus y times the vector negative 2, 3, 1. Can I write that in matrix form? Yeah, I can write it like this. 1, 0, 1, negative 2, 3, 1, x, y. So elements of H are linear combinations of these two vectors. So if this is the matrix A, then H is col A, which is a subspace. You could also say another way to show that H is a subspace of R3, we could have done this in the last class. So, or you could just say H is the span of the two columns, 1, 0, 1, comma, negative 2, 3, 1. Both of those methods show that H is a subspace of R3. You can show it's the column space for a matrix, or you can show it's the span of a set of vectors. I did it the first way because that's what I wanted to do. I wanted to demonstrate col A. Okay, another example. Here's a matrix A, and a vector W, we want to ask two questions. One, is W in null A? And two, is W in col A? All right, so is W in null A? Another way of asking that is A times W the zero vector? Because if you're in null A, that means A multiplies by U and sends U to 0. So we just need to check AW and see if it's the zero vector. 1, 2, negative 1, 1 times W is 5. So it's already not looking good. And then 1. So that's not 0, 0. So the answer is no. Okay, is W in col A? So let's think of col A as the span of the two columns of A. C1 is 1, negative 1. C2 is 2, 1. So another way of, if I rephrase this, the question is AX equal W consistent? Is there an X such that AX is equal to W? So we know how to answer that. We're going to reduce A with W, augmented with W, and see if we get a consistent system. If we do, that will give us the weights in the linear combination. So AW is 1, 2, negative 1, 1, and W is 1, 2. So we're going to reduce, leave the top row alone, add the first row to the second row, and replace the second row with that sum. Okay, now what I'm going to do is divide the second row by 3. All right, and finally, I'm going to multiply the second row by negative 2, add it to the first row to kill off that 2 above my pivot. That's 0, negative 1, 0, 1, 0. Whoops, not 0, 1. Okay, so I'm getting a consistent linear system because I'm not getting an all zeros and then something non-zero in any of the rows. So this is consistent, yes. And so write W as a linear combination of the columns of A. So my solution here is x2 equal 1, x1 equal negative 1. Those are the weights in the linear combination. So W is negative 1 times the first column of A plus 1 times the second column of A, which is negative C1 plus C2. And just to be safe, let's just check that. Is W, which is 1, 2, actually equal to negative C1, which would be negative 1, 1, plus C2, which is 2, 1. Negative 1 plus 2 is 1, and 1 plus 1 is 2. Yes. So W is in col A. All right. Next one is H equal to the set of vectors in R2 that satisfy this requirement, x minus y is 0. Is this a vector space? I would say yes. Think of this as a linear system. It's got one equation in it, but it's a homogeneous linear system. In matrix form, this linear system, x minus y equals 0, in matrix form is 1, negative 1, x, y equals 0. It's a 1 by 1 matrix. If A is this 1 by 2 matrix, 1, negative 1, then H is null A. So it's automatically a subspace of R2. Subspaces are vector spaces in their own right. So the answer is yes, because H is equal to null A. Okay, so let's compare null A and column A with a specific example. And then I've got a practice problem for you to do, solutions at the end, but you should pause the video and do that out. And then I'm going to recap with just a general comparison of null A and col A, but we'll do a specific comparison here. So A is this matrix. A is 3 by 2. So I want to think of A as a map from R2 to R3. So col A is a subspace. Col A lives over here in the target space, R3. Null A lives over here in the domain, R2. Find a non-zero vector in col A. Col A is the span of the columns of A. So I could just pick any column of A will be in the span of the columns of A. So I'm just going to pick a column. 1, 0, 0, that's in col A. So I could pick or 2, 0, 0, or any linear combination of those two vectors. But it's easiest just to pick one of the two columns. So that was very easy. Find a non-zero vector in null A. I say non-zero because, of course, 0, 0 is automatically going to be in null A because A times 0, 0 will be the zero vector, but we want a non-zero vector. So we want a solution, a non-zero solution of AX equals 0. So we're going to augment A with the zero vector. 1, 2, 0, 0, 0, 0, 0, 0, 0. Now this is already in reduced echelon form, so there's really nothing to do except write down the solution. We've got two variables, x1 and x2. There's no pivot in the second column, so x2 is free. x1 is not free, it's negative 2t. So solutions look like t times negative 2, 1. I just want a single non-zero solution, so I could pick any value of t that's not 0. So I'll take t equal 1. X bar is going to be negative 2, 1. There's a non-zero solution of AX equals 0. So it's harder to find a vector in null A. That required some work. For a vector in col A, you just pick a column. All right? And then here's a question for you. It's very similar to this one, 2 by 2 matrix and a vector W. You answer two questions. Is W in null A? Is W in col A? So I want you to answer those two questions for this matrix A and this vector W. All right. So recap. A is an m by n matrix, so I want to think of A as a mapping from Rn to Rm. Null space lives in the domain Rn. It's a subspace of Rn. Col A lives in Rm. Null A is defined, my choices are implicit or explicit. Implicit because it's solutions of AX equals 0. That's a description, but it's not saying these are the solutions. It's telling me how to find the solutions. It's telling me how to find the vectors. I have to solve AX equals 0, but that doesn't explicitly state what the solutions are. Whereas col A is defined explicitly, it's just the span of the columns of A. So of column C1 through C, how many columns are there? There are, if A is m by n, there are n columns. Okay, how do you find a vector in null A? You solve AX equals 0. How do you find a vector in col A? Quickest way is just to pick one. Pick a column. Pick a column of A. That'll be in col A. If V is in null A, then what? Well, the only thing you could say is that if V is in null A, AV is 0. If V is in col A, then what? Well, the only thing you can say, if V is in col A, then AX equal V is consistent. It's got a solution. And then finally, null A is the 0 vector space if and only if AX equals 0. Well, this is the set of solutions. So if the set of solutions is only 0, if AX equals 0, has only the trivial solution. And col A is all of Rm if and only if AX equals B is consistent for all B. So there's a summary of the comparison between null A and column A. And again, I'm remembering now, after we talk about basis, which we will, we'll talk about row space, and we'll also compare, we'll have 3 major vector spaces. We'll have the null space, the row space, and the column space. All right, let's do some true false. And that'll be the end of the lecture notes. The null space, so you should pause it and see if you can do these. The null space of A is the solution set of AX equals 0. That's true. The null space of an M by N matrix is in Rm. That's false. The null space lives in Rn. The column space of A is the range of the mapping that takes a vector x to AX. That's true. That's a linear transformation language for column space. If the equation AX equals B is consistent, then col A is all of Rm. That's false because there's a missing set of words here. It has to be consistent for all B. If it's consistent for all B, then col A would be all of Rm. Col A is the set of vectors that can be written as AX for some x. That's true. Col A is the set of vectors B such that AX equals B has a solution, which tells us that 6 is false. Col A is the set of solutions of AX equals B. That's false. The solutions are the x's. We're interested in the b's. So col A is set of B such that AX equal B is consistent. So we want the b's, not the x's. And finally, the column space of an M by N matrix is in Rm. That is true. All right, and that is the end.